during this cold winter stretch. Welcome to another one of our winter webinars. Today, our topic is on crop water use efficiency and soil moisture management in dry years. My name is Tice Masich, and I'm a crops extension specialist with the Ministry of Agriculture based out of the Outlook office, and I will be chairing today's event. CEUs are being offered for CCAs on this webinar. In order to get credit, you have to watch the entire live event, and at the end of the presentation, a QR code will be shown on the screen for you to collect your credit. Before we start the formal presentation, I have a few items to share. The Crops Extension Specialists put on this winter webinar each year. We work out of 10 different regional offices in the province, and there are multiple specialists in each office. And we are here to answer any agricultural-based questions that you may have. In order to connect with our specialists, you can reach out to the Agriculture Knowledge Center through the phone number on the screen. There are 8 agri-arm sites located throughout the province that are dedicated to bringing the industry Saskatchewan-specific demonstrations and information on new and existing agricultural practices. If you're interested in learning more from them, you can follow the QR code on the screen. If you have ever heard the words on the radio, Saskatchewan is 98% complete harvest this week, you have likely heard of the Saskatchewan Crop Report. We'd like to thank our existing crop reporters, and I highly encourage anyone who's not currently a reporter to sign up through the QR code on the screen. I also want to mention that Crop Diagnostic School this year will be hosted in Scott, Saskatchewan on July 23rd and 24th. More details about this event and agri-arm field days are to come in the future. Please note that we will be sharing an upcoming schedule on our crops for our crops webinars, but in the meantime, you can check out the invasive species webinars put on by our agri-environmental specialist team running at the end of February. Lastly, we want to make sure that everyone is aware of the funding available through the Sustainable Canadian Agricultural Partnership. You can reach out to your local agricultural program specialist to find out what funding you may qualify for. Along with this information, we will have additional resources for everyone under the handout section in the chat box of the toolbar. These will be shared along with the recordings after the webinar is complete. Today's presentations will be followed with a live Q&A with Phillip. The main hub for today's webinar today will be on your webinar screen as mentioned, and we will share relevant downloadable handouts with you in the chat box area. The entire session will be recorded, so if you miss anything or wish to revisit any of the content, you will be able to do so. Recording links will be sent out later this week in a follow-up email. An evaluation will pop up at the end of the webinar this morning. Please ensure that you fill out this evaluation to help us determine future topics for our webinars and research priorities in the industry. We have a few housekeeping notes to keep in mind during the webinar. If anyone has any questions during the presentation, you may type them in the box at the top right-hand side of your control panel. We will try to get to as many questions as possible. Your question will remain anonymous and will only be sent to me. During the presentation, you will be muted so that we can ensure that there is no feedback or interference with the audio during the presentation. Now let's get started. Phillip is the Research Director and Hydrological Scientist at Croptimistic Technologies. He grew up on a family farm near Saskatoon and he studied hydrology at the University of Saskatchewan. His research interests focused on understanding the relationships between snow, hydrology, and agriculture on the Canadian prairies. The overreaching motivation of his work is to develop understanding and tools to improve agricultural outcomes and reduce water-related risks for Canadian producers. So with that, we can get started whenever you're ready, Phil.
All right, thank you, Tice. Yeah, so today we'll be obviously getting into some crop water use efficiency and sort of kind of a broad picture of from a hydrological perspective, how crops are using water, where it's coming from, and kind of that bit of more of a hydrological context to understand what you're seeing in the landscape during the growing season. So yeah, as mentioned, I spent a bunch of time at the university prior to um, joining Croptimistic last year, and so a lot of this presentation comes from my academic work, looking at crop water use efficiency, water availability, egg water interactions, but also now getting into, as I switched over to Croptimistic or SWOT maps, looking at the precision ag implications of how do we use information better to make better decisions. So to get going here, there we go. There's kind of sort of four questions that I'll throw out there that we'll try and get through in the next little while. But broadly, what is crop water use efficiency, and what are the major controls behind it? And then, okay, so we know what it is, but how do we define or quantify it? So that is important, especially when we are trying to interpret information that we're getting from different sources. Ultimately, what is water use efficiency of different crops that we typically grow in the prairies? Um, and really, at the end of the day, so what about crop water use efficiency? But how can we use it to improve our outcomes with knowing more about it? So crop water use efficiency, start with some definitions, but really it's how we relate crop production to water use of a plant. So it's a ratio. So crop production, however you want to define it, because there's different ways of defining what production is, divided by the amount of water that was used. So, if you're looking at sort of an agronomic crop kind of sense, it's going to be, bushels per acre per inch of water is often thrown around. But water use efficiency of forages are also important, or silage, and that's going to be more of a biomass rather than a grain yield, for example. And it's a good number to have, if you want to compare things between crop types or cultivars potentially. It's important information when you want to think about environmental responses, evaluating different agricultural management practices, but ultimately as well, it's going to vary with climate. And so this is a very, on the right side, you've got this very simple representation of it. So crop production is on your y-axis, however you want to define it for your different crop types. And then on the bottom, you've got transpiration or evapotranspiration. Basically, how much water did your plant use in that period of time? And then that relationship kind of starts off with, and there's different ways of representing it, but generally, you're not going to have, you need to have a certain amount of water before a plant is actually able to grow. And so there's a bit of a base level that you need to exceed before you actually have a viable crop that would actually produce anything of value. And then after that, we often represent this thing as just a very much a linear increasing line. Um, but where we put numbers to this is where it gets a little bit more interesting. So there's a lot that's going on with crop water use efficiency, and I'll just sort of state right out from the front that I'm coming from this from much more of a hydrological perspective, and so there's a lot of physiology, there's a lot of biochemistry going on within the plants. We're going to kind of leave those aside a little bit more and talk more of like the physics behind, where the water comes and where does it go. So, crop water use, it's it's transpiration. So the water that moves through your plant that ends up doing photosynthesis in the leaves. Um, and there's a lot of controls, but really crop water use is going to be a function of how much water is being demanded by the atmosphere. So a dry air is going to exert a much larger pressure gradient on water within a leaf. And so the drier things are, the more demand there is from the atmosphere to suck that water out of your plant. And then your plant, on the other hand, is trying to resist that because it wants to maintain as much water inside through stomatal regulation. And so this is a very overly complicated diagram to show basically that, we have water in our soils that has to move through our plant. It does a lot of things, obviously. It's bringing nutrients into the plant. It's maintaining all sorts of thermodynamic relationships. And yeah, there's a lot going on, but we can talk about this instead of getting into the nuts and bolts of it much more in terms of just pressure gradients. So if there's available water in our soils, it doesn't take a lot to pull the water out, and that pressure gradient, it's like a straw that the plants are sucking on, pulling the water to the leaves, for example. So kind of have to think about this a little bit more from the physics side, and this is coming down to energy. This is how warm things are, how much sunshine there is, how much wind speed there is for mixing, and then how much our atmosphere is able to actually demand water from a plant. And so this all boils down to, the stomatal level at the end of the day. So on the underside of your leaves, you'll have these little, every plant will have different, I'm not exactly sure which plant this is, but you'll have these little cells, cellular bodies, um, which open when there's water and they can survive and they can transfer gases in and out, or they'll close and resist water movement. And it's these little gatekeepers that really mess a lot of our understanding up, because you're linking a lot of physics, linking a lot of biochemistry, you're linking a lot of plant physiology into these little stomata. But that doesn't mean we shouldn't try, because we do know sort of some basic principles of all of this. So like this all boils down to photosynthesis, where at the end of the day, for your plant to produce energy, it needs to take energy from the sunshine, combining that with CO2 and H2O, to produce, to assimilate carbon into our cells. And so to do that, you need to have this transfer of energy, this transfer of gases from your atmosphere, which is high CO2 content, to a low CO2 content within your leaf. But in doing so, you open it up and you're also releasing water vapor from within. So it's this whole back and forth, this balance that needs to be maintained for a plant to thrive, and to meet its, fundamentally, optimal water use efficiency. Uh, the thing is, there's a lot of demands and there's a lot of things that will change conductivity. And when we look at what's happening in the landscape in a given moment, it's not a nicely, tightly controlled laboratory experiment. Everything is changing all the time. And so this is kind of a conceptual perspective of how, if we could isolate the controls on stomatal conductivity, or AKA the ability for a plant to transpire water, pass water through its stomata, um, there's a couple different things going on. So the top figure on the top left, this is basically light, so how sunny it is. So no surprise, if you have no sunshine in the middle of the night, your plants are not actually photosynthesizing. Therefore, they will shut down their stomata, maintaining the water for when there is energy. So when you don't have a lot of light, you don't have any stomatal conductivity. As things get brighter and sunnier, you definitely have this increase in the stomatal conductivity, but it does taper off. So this is kind of the y-axis, is looking at 0 to 1, so no conductivity versus, unrestrained conductivity. So you need light to have photosynthesis and transpiration. The next one is looking at temperature, so your air temperature. And this is just a generic plant. Every plant has its own optimal temperature response curve. But what this is saying is when things are cold, your plant isn't going to actually do a lot of transpiration. It's going to be basically trying to protect itself. There's not enough energy. And so you'll have low stomatal conductivity, low transpiration. When you get to that sweet spot for whatever plant, you're going to have unrestricted stomatal conductivity. But as things warm up again, as basically your atmospheric demand increases beyond the capacity of your plant to sustain things, and also the heat feedbacks, you'll have a decrease in conductivity as well. So there's kind of a very clear inflection point when it comes to your air temperature and what your plant is able to tolerate. Every crop type is going to be different. And so think about like cool season crops versus warm season crops. Cool season crops, we're just shifting that curve to the left. Your canolas are more to the left than your wheats, which are a bit more adapted for your warmer temperatures. The other one here on the bottom left, this is just vapor pressure deficit versus conductivity. This is a fancy way of saying of how dry is the atmosphere. So in hydrology, we talk a lot about gradients. So pressure gradients, temperature gradients, all those things, vapor pressure gradients are really what drive water movement. So within a plant, it's generally saturated, is the assumption that is made, while your atmosphere tends to be unsaturated. So if you have low relative humidity and high temperatures, you potentially have a much lower water vapor pressure deficit. Water vapor pressure outside of the plant, which becomes a water vapor pressure deficit. So the bigger this deficit, the more thirstier the atmosphere is. And basically, this is what the response of the plant to saying, yes, the atmosphere demands more water, but I need to restrict it because I need enough water within my cells, within my leaves, to actually still do photosynthesis. So that's this decreasing line that you see there. And then this other line looks very similar as well, and this is just a response to average water stress, another word to say how dry is my soil. So if there is no water in our soil, we have low stomatal conductivity because the plant is just shutting down to retain whatever water it can. It's going to basically conserve water at the expense of productivity. And so when this is the situation that happens, this is when you start seeing really big declines in water use efficiency. Because when the stomata shuts down, transpiration shuts down, but it does not affect evaporation, for example, which keeps on going. So this is kind of the fun term that's thrown around with this is the transpiration paradox. So a plant, it requires CO2 from the atmosphere, but in doing so, it loses water vapor, which it would also like to retain to do more photosynthesis. So it becomes very complicated very quickly, and it's really this moderation. We want to optimize things. The plant is doing the best it can to stay alive, to produce as much, but also not die. And the one way you can really look at this and to assess this is looking at a crop in terms of its thermal, the surface temperatures. So this is a crop on the top. This is just the aerial image from a drone. So this is an irrigated canola on the top left, and right next to a dryland wheat that was really suffering in this particular year. And if you look at the corresponding temperatures associated with this, we have air temperatures on the order of 25-ish temperature degrees Celsius, which is really very close to the air temperature at this time. So this thing was well watered. It was able to basically reduce the amount of um, heat because it was transpiring versus our dryland wheat here, which was clearly did not have enough water. It was also at a different growth stage. It was getting towards more senescence, so it really wasn't transpiring much to begin with. And it was getting quite hot. We're getting upwards of, 40, 50 degrees Celsius on the surface. And so this is kind of where, if you look at this a bit more, you can start understanding what's going on with your crops. And so in an ideal situation, to maximize productivity, you want to be in a scenario where you are energy limited, where you have more water than can be just immediately taken up by a plant. And so this is a well-watered situation. This is an irrigated situation. And this is looking at a thermal image of from the same perspective, one being the optical regular camera photo image, and the one on the right being a thermal. And you can see how on this day, the air temperature is around 30 degrees. So SPI 1, spot 1, it's at 27 degrees Celsius, which is a nice green looking plant. It's at air temperature. It's not when our plants are at air temperature, that generally implies that they are going to be using water in the most optimal way possible. You look in the shadow, and this is where we have evaporating water from the soil, so it's cooling down things even more. So it's 24 degrees there, while our black soil, even though it's wet, it's still black, and it's at 37.8 degrees. So in this scenario, the more cover we have, the more energy is going straight to the plant and going straight to transpiration. While in this area where we have uncovered plant and any wet soil, it's actually still going to be evaporating quite a lot. The flip side is a water limited situation. So this is generally going to be a dry land or a drought situation, a water deficit. And what happens there is that your plants, they're doing their best they can, but really the transpiration by itself is unable to regulate your temperature and the heat stress on your plant. So when water evaporates, whether it's through transpiration or from the soil, the molecular bonds holding your water together into a liquid form need to be broken, and so in doing so, they need to absorb energy. So when you get out of a shower, for example, you feel cold. It's because your water is evaporating. It takes energy to evaporate, and so when a plant is transpiring, it's using up a lot of energy, and that's why it's cooling down. So in this scenario, similar kind of situation, we've got an optical photo on the top and a thermal photo on the bottom. This crop is clearly in more of a senescent stage. It's not actively growing in the same way as a green plant would be. And you can see quite quickly that it was the same day as the previous situation, and these are 200 meters apart, these points. But our SP1, this is our wheat, it's at 35.6 degrees Celsius, so it's warmer than the air temperature already. Um, and then our dry soil in this situation that is fully exposed in the sunshine, it's actually at 63 degrees Celsius. So it's incredibly intense. So just because it's 30 degrees out doesn't mean that that's what your soil temperature is if it's dry and dark. You can routinely get soil temperatures 60s and 70 degrees at the surface. And that's going to have implications for, soil health, for example. Um, the fun part about this also, which probably makes a lot of people cringe, but we have this wonderful kochia plant that's also decided to grow in this field, and same conditions, but clearly it has the ability to withstand these stressors in much better than our wheat. So SB4 in this case, it's at 32 degrees Celsius, so it's very near the air temperature. It's able to basically hold on to water much more effectively and conserve it much better than our wheat. So I don't know, for all the wheat breeders out there, we just need to get more kochia genes, I guess, into our wheat. Um, so there's a bunch of interplay and feedbacks between what's going on with water to use efficiency. So the question is, how do we quantify it, really, or how do we define it even? So there's kind of two ways that I see and that I've encountered. So there's one where we're talking about agronomic water use, and this is where we're talking about yield per unit of evapotranspiration. So this is going to be a number that you get once per year. It's a seasonal estimate. Um, and then there's another approach where it's like, well, what about more of the physiological kind of way, physiological water use efficiency? And so this is where instead of looking at the yield you get at the end of the year, let's talk about how much carbon was assimilated. So how much photosynthesis occurred. So how much carbon ended up in our above ground biomass and our below ground biomass. And so what this allows us to do is look at um, it really normalizes between crop types. And you can also start looking at, depending on the instruments you have, how water use efficiency changes over the course of the year. So there's kind of two ways. The traditional approach, that agronomic approach, we often look at sort of a yield, and then we look at sort of a water balance. In this case, often we look at, the rainfall that occurred during the season and our change in soil moisture, and that we add those two together, and that's a crop water use. And then we have our yield from our yield monitors or samples that we take in the field, and we divide the two that way. The challenge is that, you know, this is in 2021 at the Livestock and Forage Center for Excellence. Um, there's huge amounts of spatial variability in the landscape. And so in this scenario, we had parts of the field that had burnt off quite early on, yet we still had low spots that were just trucking away. So what is the water use efficiency of this field? Where do we measure it? How do we do it? And you can't really do that with points-based or even point-based methods that you would get from a water balance approach. So the one thing that we did that we had access to at the university was a system called eddy covariance. And so what this does is it uses micrometeorology principles to basically directly assess crop or water, the net water exchange between the atmosphere and the surface. and it looks kind of at an upwind area. So the wind that is flowing past the air that's flowing past the sensor, it represents an upwind area, and so we're able to say come up with field average estimates of crop water use. And the other wonderful thing about it is because it's just looking at what's happening in the atmosphere and the net exchange, it doesn't really matter where our rooting depths are. So if you look at a soil moisture probe, sometimes you have to make an assumption of this is how far my plants are actually accessing water, because you don't want to look at too deep. If it's a shallow rooted crop, to know how much water use changed in their soil profile. And so this kind of skips that a little bit. Um, so it's a great, fantastic tool, but it's a research level piece of equipment, and not something that we're normally going to put out in a lot of situations, but it can tell us a lot of information. That's what we'll get into shortly. So, what is the water use efficiency of prairie crops? And does it vary? So this was some work that we did through the university. And so this is looking at, we had data going back to from 2015 to 2021. Some crops were counted in multiple years, but we had about, I can't remember now, 19 or 21 site years of information. This is a small subset of data. It's not going to represent every single condition on the prairies, but there's kind of two things to look at here. So if you look at the dots that have the circle with the cross through it, that's using the water balance approach. So we had a soil moisture profile in one location, we had a rain gauge, and then we looked at that as that's our water use, and then we looked at the field average yield that was coming from the harvesting equipment. And so you can see quite quickly that there is a big spread when we start looking at our water use efficiency from that perspective. In contrast, we have these solid dots, and these are our field average estimates of water use efficiency from the eddy covariance. And so there's two things to note. First is when we look at that water balance approach, that point scale information of soil moisture, we get a really big spread in water use efficiency. In contrast to when we have that field average estimate from eddy covariance, where that range really drops down. And so that's interesting. So what that kind of led me to conclude is that when we look at just water balance based point scale in pieces of information to come up with a water use efficiency, they're not always representative. There's a lot more variance that we'll see in it than if you had another more independent method that looked at field scale ways, and there's a lot less variance between. So there's the other component of this is that the intra-crop water use efficiency is actually relatively low. We have more variance between crop types than within crop types. So barley, it had a fairly low water use efficiency. Wheat had a greater one. Canola had the lowest, and lentils and peas had much greater water use efficiency. But once again, remember, water use efficiency, it's a ratio of production divided by the water use. And so the key thing to remember is that lentils and peas, for example, yes, they've got great water use efficiency, but they're the most shallow rooted crops that we grow. So they're not using as much water. Canola, wheat, and barley, they have much deeper roots, so they're able to access more water and therefore produce more, even if they have lower water use efficiency sometimes. The other key thing to note is that canola, in this sense of agronomic water use efficiency, it's quite low because the harvest index, the amount of biomass that comes off of a canola crop that as seed, as that marketable yield, is much lower than a barley or a wheat or a peas. So that's what skews that water use efficiency lower. So I kind of mentioned before the seasonal sort of physiological water use efficiency. So this is, looking at, how much water is used to assimilate a unit of carbon. So the great value in this one is that we can start looking at different crop types, and we can forget about the differences in harvest index. And we see, well, what plant actually grows the most, biomass. And this is a good way to, let's say, look at, more of our forage crops or our silage crops. So we can start plotting those on the same figure. And for the most part, there's not a huge variance. There is variance, but there's not that same between crop type variance in water use efficiency. Um, the key thing to note in here is that 20 and 21 was this pink dot. And so this was the one year that we actually had observations of corn. I would not put a lot of stock in it. Um, but other than to say for our corn, it had the highest water use efficiency of a year that was absolutely dismal to begin with. This is the year where we had the heat dome and we had great thermal stress that showed up all of, out of nowhere early in July. There was actually still some water available, but we just got to the point where there was so much thermal stress that the plants just shut down and died um, because they couldn't meet that extreme water demand. So take those pink ones with a grain of salt. And the other component to look at is that our forages, they also have the least, if you forget about the pink, they tend to have the least water use efficiency. But once again, just keep in mind, forages, they're perennial crops. They have much deeper rooting depths than our annual crops. They start off with a rooting depth that is quite deep. They don't have to grow their entire root profile in that growing season, and they're using water as soon as the snow melts. And so, yes, they have lower water use efficiency, but they can withstand a lot of other things, a lot of other stressors that our annual crops clearly cannot always. So another thing to look at is, how does water use efficiency change over the growing season? So this is going back to that physiological one because with our covariance system, we can look at what is our water use efficiency on a particular day versus what's the seasonal average. And there's a lot going on in this figure, but the key thing to look at is the slope of the line. So the slope of the line tells us the steeper the slope, the more efficient it is in terms of water use. And so, early on in the growing season, when we really don't have much in the way of any crop, bio leaf mass, surface area, to actually do a transpiration through, we have pretty flat lines. So basically, all the water use that's happening prior from emergence until a leaf out stage, that's just soil evaporation that's happening. That's what's changing our water conditions in our soils. Um, the plants, yeah, they're using some water, but it's negligible compared to what our evaporation is able to move through the atmosphere to the atmosphere. And then once you get into vegetative growth, this is when we start having canopy closure, we have more leaf area and flowering. We have, and even the filling stages, um, we have much greater water use efficiency because now our canopy of our plants are growing. We're able to actually transpire water. We're sheltering our surface with shades that's not getting as much energy to evaporate. We're much more effectively hammering water through the system. And then by the time we get to maturity, when things start senescing, that's once again where we're not really using a lot of water for our plants. What the water that is being used is primarily through evaporation. And then if you contrast, these are our annual crops. And the bottom row here is our forage. And another thing to note there is it's much more muted. We don't have that same increase in peak with our water use efficiency, but it's consistent throughout. Even in this one, crop phases don't really make as much sense. So this is May, June, July, August, and September. We have water use that goes into assimilation of carbon, throughout the year. So yeah, slow and steady wins the race when it comes to forages. So the question that often comes up as well is, well, has water use efficiency changed over time? Um, and as I've kind of shown you already, it really matters how you define water use efficiency, what the methods you use, and even the units. And so this is kind of going back into the literature, looking at Canadian prairie studies. Um, and what were the water use efficiencies that were reported? And at the end of the day, there's a huge range. And so if you look at the study that we did during my academic time, this is in the observed column. These are the average values that we observed. And then you look at the literature for values that reflect similar conditions. This is limited to Western Canadian prairies except for lentils, which were clearly an increase in water use efficiency, well outside what was observed previously. Everything else falls within the bounds. And so this really comes down to number one, conditions are variable, and water balance approach has a ton of limitations. And so what we're actually able to represent may not actually always be most appropriate. And so you have to approach water use efficiency numbers quite carefully depending on how they were determined. The thing with lentils is that, at the end of the day, what's really gone into increasing their water use efficiency is that plant breeding has really pushed the harvest index up. So previously it was on the order of about 25% of the above ground biomass was the actual lentil that you would harvest. Now we're getting to closer to 50% of a harvest index for lentils. And so that's a huge gain. And that's what's going on there. So talked about water use efficiency a lot. So what can we do to actually improve our outcomes if we know a little bit more about water use efficiency? And so this is where you have to go back to hydrology, because fundamentally transpiration is equal to crop growth. And what I've tried to been conveying with what I was talking about earlier is that outside of extreme conditions, extreme droughts, assuming that your fertility is fairly, appropriate, uh, the gains when it comes to improving water use efficiency on its own, that's not what's going to get you more production. What's going to get you more production is just increasing the amount of crop available water, because that water use efficiency, it can be quite variable. It can be quite, there's many factors involved, but the most reliable thing to increase production is just to, at the end of the day, increase the bottom part of that ratio. So increase the amount of crop water availability, the amount of water that can actually go through the plant. So to do that, you kind of have to look at the hydrology behind things. So this is a conceptual diagram of uh, you know, a volume of soil in the middle of your field, so surface down to the bottom of the rooting zone, and so let's call it a meter cubed or something. So where's the water coming in and where is it going out of this piece of soil? So we're getting water that comes in through precipitation. We're going to have water that leaves through transpiration from the root zone. We're going to have water that leaves from evaporation from our surface. But in the prairies, we have things like snow, if you're aware of that, if you look out your window. Um, so we're going to have an accumulation of snowpack in the winter. We'll have snow that blows into a field, that blows out of a field. We've got sublimation from that snowpack. But when we also can have things like runoff that comes into that part of the field, leaves, or water flow through our subsurface. So if we want to increase our crop available water, we need to look at what we can do to change, that net change in runoff, that net change in flow through our subsoil, that net change in infiltration versus runoff partitioning and snow retention. So all of those pieces come into play to increase the amount of transpiration available water. So as part of the previous work as well, we looked at the water balance of growing season for several crops. And so the top row, this is for a site near Clavette. The bottom row is a site near Kenniston. And red is the crop water use from our equivariance measurements, and blue is the in-season rainfall during the growing season. And so quite quickly, you should see that, except for 2015 and 2016, we typically have a whole lot less rainfall in season than crop water use. And that's because snow, winter processes. 2015 and 2016, they were quite wet years, but even in those wet years, our water use was not less than our growing season rainfall. So plants are really good at using water, whatever water is available. And in this case, in 2017 onwards, water that came from parts of the year that were not in the growing season, so winter processes. So what's going on there? Because we often think about, oh, the ground froze, nothing's moving, everything is static. And often the conceptual model is snow will just run off anyways. It doesn't really matter, but it really does. And so this is kind of a conceptual diagram of what's going on. There's a lot of processes going on in here. But generally, yes, we have in fall, temperatures drop, we start developing a snowpack, our soils start to freeze, and they freeze and decrease. That freezing front goes further and further into our soil profile. We may or may not have midwinter melts. And then when it comes to snowmelt, we have a snowmelt event reduces the snowpack, and then it starts melting, thawing our soils from the surface, but also from depth. And there's a couple things that are going on that we have to that we can manipulate. So one thing to keep in mind is depending on our soil conditions at this freezing front, we can actually have water movement to the freezing front. And so there can be redistribution of water in our soil profile just from this freezing front dropping through it. So we can have movement of water closer to the root zone from that mechanism. As well, midwinter melts, they do actually infiltrate sometimes. And so you can have water infiltrate into our soils during the winter. And also, in a snow melt event, we can actually have a lot of infiltration that does occur. Um, and things like how deep is our snowpack will really also impact how deep our freezing front gets over the course of the year as well. So how quickly do we actually thaw from above and below? Because at this point, when this frozen soil lens disappears, that's when all your sloughs disappear if they can. So we have control over a bunch of these different things. Key component to remember in all this is that snow has a ton of water in it. It's not a 1 to 10 ratio. It's not 10% water out there. Because of snow metamorphosis, blowing around, all those factors, we can actually have quite an increase in snow density over the course of the winter. So I went out with my son a weekend or two ago, and we are currently near Clavet here near Saskatoon at about 24% water content in our snow. It's going to get more, especially as it gets wetter and it melts and um, infiltrates within the snowpack and refreezes. So when it comes time for final snow melt, it's quite often we'll see 35 to 40% even water content before any water actually gets into the soil. So if you've got a foot of snow out there, you've got 25% water content, we're looking at 3 inches of water. And I think this year that would be a low number. Right now where I'm sitting, we've got about 4 inches of water in the fields. In the more wind-blown areas rather than the drifts. So how do you control this when water is in our snowpack is so important? Well, it comes down to managing your blowing snow. So this is you know stubble height is the factor that matters. So the taller your stubble, the more snow it can trap. As soon as snow is moving around on the surface, it's also sublimating. And so in this scenario, we had sublimation, blowing snow movement with those dunes marching back and forth for 3 months before our taller stubble filled in. In that period of time at this location, that ended up being about 12, 13 millimeters of water, which wasn't a lot, but it does matter as we get into, is that enough to push you over that threshold to get to, good production versus struggling production? So anything you can do to increase your the roughness of your surface, basically stubble height, will increase the amount of snow that can be retained on the surface. This year is a great year for retaining snow because there's so much. If there's no snow, obviously that's a different story. But looking at this as average response of total melt for an increase in stubble height at Swift Current in Saskatoon, on average, you're looking at about a centimeter stubble height is equal to another millimeter of water, but that's an average response. This year, we clearly have most of our fields, except for more extreme situations, they filled with snow months ago already, and we don't have that same inflection point. Sort of the extreme end point of all of this is things like stripper stubble, where you can have really high stubble heights. And so, this is from 2023 near Consort. We had a 75 centimeter tall stubble next to a lentil that had basically no stubble. And we had 110 millimeters of snow water equivalent. So that's the amount of water in the field versus 41 in that lentil stubble. But to be, transparent, that lentil stubble, it had fresh snowfall on top. And the next day, I believe there was a bunch of wind. And so a lot of that would have just blown away anyways. So there's very stark differences in the amount of water that's in our snowpack. Um, and if you're looking at some of those years where we had minimal in-season rainfall, 110 millimeters of water equivalent, that's more than what fell as rainfall in the year. So this is a significant component sometimes. So while snow on the surface is great, it doesn't always make it in. Obviously, frozen soil infiltration is a bit of a beast. Um, so there's kind of three ways of looking at it. One is everything will go in an unlimited scenario. This is when we have really dry soils in fall, when things are cracked. We've got really coarse or permeable soils. Snow melt is a slow release kind of situation, and the conductivity of our soils, even in when we are dry and corked and coarse and cracked, um, they're able to accommodate it, and everything will go in. The scenario that we typically don't want is a restricted situation where you have a saturation layer that forms from late season rainfall right before freeze up, and so you'll get this concrete frost, this saturated layer. So no matter how dry it is beneath, you won't get any infiltration that goes through. Or you have a snow melt event in the middle of the winter. You have water that percolates through your snowpack and then refreezes at the soil surface. So those are bad scenarios when it comes to infiltration potential. In reality, we live kind of between those, and so it's limited. So basically, how wet were things in the fall? The degree of saturation of your soils will tell you basically how much is able to get in, as well as the duration of snowmelt, which is really a proxy for how much snow there is. So this year we've got a ton of snow. Even if we have midwinter melts, generally they're not going to get to the point where they're able to actually melt enough to percolate enough water through the snow to then refreeze because of all the insulation that we've got to deal with first. And so for the most part, if we had dry conditions in fall and a bunch of snow like we have had now, we're very much on the limited situation or even unlimited situation when it comes to snowmelt. So our yeah, potential is great. So stubble is really good for telling you how much snow you can retain, but residues is really where it's how much you can. Sorry, stubble is really good for maximizing the amount of water on your landscape. Residues are really for maximizing retention of whatever water has made it into your surfaces. Um, you're always going to have some soil evaporation, but residues can really tamp it down a lot. There's a rule of thumb that around every 10% increase in surface residue cover, you're going to have about a 5% decrease in evaporation rate. It varies. That's a very rough number, but it's mostly just to give you a little context. So it's kind of a bit of a thought exercise we did. How much can we actually change crop available water in the context of knowing how much was actually used in certain years in certain locations and having good information on how much snow we actually were able to retain. So the question we kind of put out in this paper that we wrote was, if we were able to if we were able to retain all the snow between what we observed we were able to retain and what fell as snowfall, and then also how much could we increase water retention if we um, reduced our evaporation and corresponding to a 50% increase in surface residue? How much does that look like in terms of our total water budget? And the answer is up to 20% on average. Some years, if you don't have snow, you can't really play with that lever very much. But in years where you do have snow, you can play with it even more. So this 20% is not what happens every year. But that's the order of magnitude that you can change crop available water on. So about a fifth of your production could be affected by how you manage your surfaces in terms of residues and crop stubble. So how do you go take this the next step though? So at the end of the day, there's a lot of uncertainty when it comes to soil moistures. But at the end of the day, it's really you need to have accurate soil water information if you want to actually take advantage of it to optimize your fertility, to maximize your economic gains or environmental gains if you're trying to reduce to increase nutrient use efficiency and stuff like that. An entry point for a lot of this is often, let's get a soil moisture probe and we'll stick it into the ground and see how much water there is. And that's a great piece of information, just has to be interpreted carefully. Because the drier it is, the more variable our soil moisture status is, the more detached from reality, from the field average, that one piece of information is. So one thing that we're doing at Croptimistic that I've been getting excited about is looking at sort of the spatial relationships and how can we, take it to the next level. We know that there's limitations of infield, point data, soil moisture, but we also have a lot of information, at least from the Croptimistic side of things, of the spatial variability of soils. And so, this is, a classic SWOT map. So we've taken the soil, water, and topography potentials and delineated zones based on those. And that's great for, categorizing relatively within the field where these things should be producing better and how we can target our fertility. But the one thing we can do to take it a step further is to take what goes into those SWOT maps to actually come back with, something more quantitative in terms of like what is the water holding capacity of our potential root zone. So soil properties vary across a field, and this is not the most the starkest example, but our hilltops clearly have a whole lot less water of it holding capacity um, that would be plant available in our root zone than in our depressions. And then taking a bunch more water balance information, run it through a hydrology model, we can start getting ideas on, well, what is the actual plant available water at a particular point in time? And you can see how much it varies from on the order of 10, 12% water holding capacity, available water in a depression right next to a hilltop that, it's getting more like 4 or 5% available water. So this is an example from this past season. It's a canola crop near Saskatoon. And there's this typical landscape pattern that you see: drier on hilltops, wetter in depressions. But the key point was like this past year, we went from really wet in the springtime to all of a sudden the taps turned off in July and everything just dried out across the landscape. And what that really ends up showing us is that, yes, we have, um, this shows us the limitations of looking at sort of fields on an average situation. So we have these different zones. So zones 1 to 2, 3, those are more of our higher elevation, drier locations. 8, 9s, and 10s, those are getting into our depressional areas. And in this scenario, we had, and this is based on actual observations and the modeling that goes with it, we had water stress throughout the year on our hilltops. And then we had saturation, water excess issues for a good portion of June and July in our lower locations. And so there's a lot that's going on here. And so this is another example of we can't look at, say, field average water use efficiencies with a whole lot of confidence because there's so much going on within our fields. Um, so, this is another perspective. And so like, okay, now we've got yield data on a spatial perspective, but we also can get things like crop water use information from the SWOT water model that I've been working with. And you can see how wildly different water use efficiency is across a field. And so in this field, in this example, our low areas where there was great water supply, they were much more efficient. We were on the order of 10 bushels an acre per inch of water versus our hilltops where, we were getting down to, 2 or 3. And so there's a lot that goes on with our hydrology, our water use efficiency. I started off saying it didn't vary very much, but that's from a field perspective. Where it really matters is when we can start getting into these spatial perspectives, because now we can start targeting, our fertility to these areas, more appropriately. So, what does the coming year look like in all this context? There's kind of two things that I'll always look at. Number one is what were the moisture conditions in fall, and so this is from the cropland topsoil moisture from the SAS crop reports that were given a plug at the beginning. And so for the most part, we were looking at adequate to short throughout the province. There's obviously variability within that. But what that tells me is that we weren't saturated. So going into fall, for the most part, you know, there might have been places that were a bit better than others in terms of fall moisture, but we weren't wet. And when you get into wet scenarios, that's where you have these limited and restricted infiltration situations really prop up. So going into winter, we were for the most part dry, which in the context of our current snow situation, which is this figure on the right, this is a very coarse regional scale representation of snow water equivalent. We've got a ton of snow. And so between these two situations, we're looking at pretty good infiltration potential. Likely we're going to see runoff just because that's the reality. But just because you see runoff doesn't mean that there's going to be there isn't a ton of infiltration as well. So yeah, to wrap this up, crop water use efficiency, it's really complicated. And at the end of the day, from a hydrology perspective, it's really driven by plant water availability and evaporative demand. So there's definitely been huge gains in our agronomy and our crop breeding that have allowed us to have plants that can survive a much greater range of extremes, which is great. But really, the production gains and increases come down to making sure that we can still, the plants don't die. So that means now we can grow them more through other parts of the year. Um, and there's going to be more gains when we start looking at how we can optimize our fertility and variable rate to soil water status and potential. So we need information for these things. And then, more generally, things like optimizing our stubble and residue practices is what's really going to continue to show us gains when it comes to increasing production and resilience to ag water interactions. So with that, I will leave it. Yeah, and I guess questions and yeah.
Thank you, Phil. So once again, thanks, Phil, for that presentation. It was very good, very interesting. So we have a few questions here. The first is there any work done with wind turbines stirring up air that affects the atmospheric moisture gradient and hence potential yield loss from lowered water use efficiency?
I haven't really seen anything in that respect. I don't know. I don't have a good answer for that one. I'll admit that. But in general, like wind turbines, in some ways, like it's a turbulence thing. So wind turbines, they will basically take energy out of the atmosphere from that wind flow to convert into electricity, and so there's going to be a net decrease in energy from that area, um, potentially a reduction in turbulence. And so, if anything, that would reduce evaporative demand. But that's kind of going back to like first principles. That's my answer. But I haven't seen any work that really would show anything like that.
Yeah, yeah, makes sense. Thank you. Just a quick note for our listeners. I'll pop up the CEU credit after the presentation or after the question period here. So next question is water use efficiency related to drought tolerance in each type of crop? In other words, uh, could a crop be good at using water that is available but not the best at absorbing water from the soil due to its root structure?
Can you say it again? Sorry.
Yeah, no problem. Is water use efficiency related to drought tolerance of each crop type? So, in other words, could a crop be good at using water that is available, but not be good at absorbing it from the soil due to its root structure?
Right. Okay. Yeah, no, it comes down to the definition of drought tolerance and what that means. And I'm not a plant breeder, so that's going to mean different things to me. But at a very high level, like when I look at things that are drought tolerant, they're able to withstand extremes better. When it comes down to how more can they actually produce more with less. There's definitely going to be some cultivars that can do that kind of response, but it's not. going to be a lot less than, just the overall. It's not going to vary as much as like how much water is available. It will, you know, they won't die as soon, um, but they'll still have to have water to keep on going and to actually get into, a more productive state. So it just opens your window of opportunity for production.
For sure, makes sense. Thank you for that. Next question. We have to harrow to manage crop residue. As far as retaining snow, is it better to harrow in the spring before seeding or in the fall after harvest?
This is the fun agronomy versus logistics situation. Um, if it's possible, it would always be to harrow in springtime, but it's the reality of we don't know when snow melt is and what it actually looks like. Our seasonal forecasts are not that good to give us confidence, and so if all things equal and you had the ability to, yeah, harrowing in springtime would be the preference. It will Harrowing depends how there's various forms of harrowing. Some harrowing almost looks like tillage these days, to be honest. Uh, but the kind of harrowing that you're doing, often it'll be reducing your stubble height. Um, Reducing stubble density isn't quite as big of a deal as just the overall height. So if your harrowing operation is able to still leave some standing stubble, it's going to be better. Um, but yeah, it's also like, yeah, there's advantages from a microclimate perspective of delaying harrowing as long as you possibly can.
Yeah, for sure. That's kind of what I was thinking. So thanks for answering that. In the spring, there's a lot of logistical concerns to consider. So it's definitely something to think about. So next question is, do spring conditions impact root development? I hear all the time that drier springs will create the plant or will create a need for the plant to send roots deeper. And can that be a good thing?
Um, yes. Uh, every year is different, and so it's always hard to, nail it down to one thing. But yeah, there's definitely been situations where, I can't remember which year it was, but there was some moisture the start of the year, but then we ended up having a dry layer kind of below that initial rooting zone, and then it was wet beneath, and our plants they weren't able to bridge the gap, and so there's a lot of unused water in the fields, and while yields were suffering. So yes, it's definitely a thing where if your plants didn't weren't forced to root deeply when the peak water demands hit, they're not in the capacity to all of a sudden just send roots way down because they're still trying to survive. Um, so it's very much comes down to a timing thing for a lot of these things. Because yeah, when you hit July and we have, the classic example is 2021 where we went from, it was okay conditions realistic overall to, 40 plus degrees for 3, 4 days. um, those plants just didn't have the capacity to draw enough water, and they couldn't just grow in that immediate water demand situation. So yes, there is something to be said for having, water at depth, not all at the surface, forcing those roots to go down. Because yeah, if you don't have those roots, um, yeah, the deeper your roots, the more resilient your system is, for example.
Yeah, absolutely. Next question. Can we ridge snow in certain patterns to create better catch and filtration into of the snow water melt on sloped land?
Yeah, so ridging is an interesting one. There was some work done in the 80s, and so that's, yeah, almost 40 years ago now. So like the economics are clearly different in that. So I haven't done any of the analysis thereafter, but ridging was it was deemed to be like one in 4 years it made sense. So it's not really a practice that um, would will always give you returns. There's what you're doing when you're ridging is you're creating these obviously increases in surface roughness. You're going to have increase in snow retention in certain particular areas, but it really depends on your winter conditions. And so after you've plowed the snow, did you get more snow right away, or did you have like a warm period and you had some melt that refroze in that surface? And so potentially when you're ridging, you're also reducing your infiltration capacity. So yes, you're getting more snow in that one particular location, but it may have to run a ways before it can infiltrate into an area where there is retained snow that has been insulating. So it's a really tricky thing. It comes down to the conditions. Sometimes it can pay off, and sometimes it really doesn't. You may get more snow in the landscape, but it may not actually end up where you made the ridge. You may have a lot more runoff in those where you've plowed, for example.
Yeah, for sure. Thank you. Next question. What is the effect of wetlands on soil moisture?
Um, well, it's a fun one. Uh, so I guess the context that I'm going to answer this question in is going to be, what do wetlands do for soil moisture? And because this, I'm assuming an agricultural audience and probably coming from an agricultural perspective, what do wetlands do for soil moisture where I'm able to crop? And the answer is not all that much. It depends a lot on what where you are in the hydrological conditions. So wetlands, they're really good for, taking local runoff, retaining it in place and infiltrating and recharging groundwater. So if you're in a scenario where that groundwater table is far beneath the surface, it's not really going to have any impact on the soil moisture outside the margins of the wetland. If you're in a scenario where the groundwater table is closer to the surface, you may have capillary rise from an elevated water table that does intersect the root zone outside the margins of the wetland. But those are going to be very locally constrained impacts.
Yeah, thank you for that. That was a pretty broad question, so I think you gave a good answer for that one. Next question is, water being our limiting factor, what are your top priorities to conserve water? And once again, I assume in like a field agricultural setting.
Yeah, so there's the way I kind of look at it is, number one, we want to get as much water as we can in a water limited situation. So that number one is let's retain as much stubble as we can for when we do have snowfall events, we do have blowing snow events, we can retain as much as we can. It can be a lot. So the number one is we can't change rainfall, we can't change snowfall, but we can change how much water comes in through management of the snow. So that's number one. Number two is that residue. So once we have water that's available, we don't want to lose it. So that's residue is number one, really good at reducing our soil evaporation rates. What I didn't mention as well is that the more residue you have on the surface, the more it slows your runoff. So whether from meltwater or from rainfall, it can or slow down water movement orders of magnitude. And so when it comes to infiltration, to get more water in, it's all about giving your soil enough time because it can run off laterally very quickly versus moving slowly through a profile. So the more you can do to retain that water on the landscape is important. So other things, it's like coming down to questions of harrowing, you know, if you want to get really fancy, like what is the direction of your implement traffic? Is it perpendicular to hill slopes or is it parallel to hill slopes? Um, Everything you can do to maintain water on the landscape before it runs off is always going to be advantageous because in a dryland situation like most of us are in.
Yeah, for sure. Thank you. We've got three more questions here. Given the importance of ground cover and water infiltration, is there any work or plans for work on the effect of cover crops? All the presented data was on a monocrop scenario. Is there any opportunity to expand this research to compare using cover crops such as biennial companion planted cover crops?
Um, well, I'm no longer in the academic sphere directly, so the answer from my perspective is I'm not doing any of it, unfortunately. Uh, but and I haven't seen a whole lot of it elsewhere. Not saying that it doesn't exist, but I haven't seen much. The challenge with cover crops is that often in a water limited environment, um, you know, it's not the it's going to work some years and be a gain some years versus not in others. Um, and so, yeah, everything we did was monoculture. Um, but at the same time, I often think about like in a situation where we have dry, semi-arid conditions, water limited. I think of our stubble and our residue as our cover crop. It's not actively growing, but it's doing very similar things for what we're trying to achieve with actual cover crops. Yeah, there has been some work done. There is a feedback where potentially if you're able to establish a cover crop in fall, it does use up available moisture. It does increase the infiltration capacity for springtime. And so potentially, depending on the year, you could have a net gain in soil water by having a cover crop. Um, but that's a very tenuous thing that isn't going to be a consistent gain.
Yeah, for sure. Thank you for that. There's, yeah, again, probably not too much information on cover crops relative to monocrops. So next question is, you talked about strip header stubble benefits. Is there a minimum stubble height where you don't find statistical difference in water in the snowpack? For example, if there's a benefit of going to a strip header versus leaving the stubble at 45 degrees Celsius or 45 centimeters. In addition to that question, is there a trade-off to chopping some stubble for the gain of surface residue versus taller stubble height with a strip header that would leave virtually no residue?
Right. Um, okay, two questions there, and I guess it
Mm-hmm.
comes down to, uh, you know, I showed some stuff earlier where it's like, well, if we increase stubble height, how does it respond? Um, and there is an inflection point. So on average, I would say if you're trying to balance height versus gains for snow water, it's like 30 centimeters is kind of the inflection point that kept showing up in some of our other work. But that's like on average, looking at say 1960 to 2000 climate data. I think that ran those models. Um, and a year like this, where we have most areas have a ton of snow, you're going to have more gains when you go higher than 30. But if you wanted to have a number that would work for, that would be an optimization for low snow years and high snow years, I've often seen kind of an inflection point show up around 30 centimeters. It really depends where you are in the prairies and the typical snowfall. The higher snowfall situations you're in, you get more to the northern grain belt, the higher the stubble height will get you more. Um, there's definitely diminishing returns when you get more into the southwest. And then the second question there was, oh, benefit of the residue versus chopping versus not. I guess no, you don't get the same residue that comes out the tail end of a combine from a stripper header, but it depends on your rotation and how you manage it in between. Like you do have a development of a, you know, thick residue, I don't know, almost thatch layer, depending on how you do it and your rotations that are involved. So, uh, and also by having a much taller stubble height like that, um, you do diminish the evaporative demand at the soil surface considerably, just because you've slowed down the wind speed so much, they're shading, and so you don't really actually need that same level of residue to maintain to reduce your soil evaporation in the same way. The question of, when should you do one or the other, it comes down to your rotations and where you are. If you're in a scenario, where you don't have a lot of snow, the answer is going to be probably go a little heavier on your residue than your stubble height. Um, and if you've got a ton of snow, um, yeah, it depends on where you're at. There's no good answer.
Yeah. Yeah, no, absolutely. Yeah, thank you. Thank you. Sorry, I threw two questions there at you at once there. But yeah, thanks
Nice.
for all the answers. So we got one last question here. This one's a bit of a shorter one. Any thoughts, do you have any thoughts on using crops like tillage radish to increase water filtration and reduce compaction?
Um, yeah, no, I think if you can get those things growing and if it makes sense in your rotations and yeah, absolutely. When it comes down to getting water into your soils and getting it distributed through your soil column, you need things like macropores to overcome compaction issues. And so those tillage radishes or whatever, what other deeply rooted type things that can form those for you, the better. Um, how you implement it, that's going to be, you know, very uh, diverse and how then locally specific. But absolutely, those things can make a huge difference. Will they give you like a net economic gain over X amount of time? Maybe not. It depends on your soil types and what tillage, what compaction or other issues you have, and how well you can establish these things. Um, but with most things, when it comes to like trying to manage your hydrology, your soil water interactions, like it's a long term project. You're not going to get a gain in 1 year. It's a system, right? You have to adapt your system, and responses and gains from a system change always take a long time.
Yeah, absolutely. So that was our last question. So once again, thank you for your presentation, for answering all those questions. Uh,
Hmm.
right, uh,